So I apologize in advance if my voice is a little off in the beginning of these videos because I'm still getting over a cold. Just if I start coughing randomly, apologize. I'm going to try to edit it out the best that I can. So where we're going to start is we're going to begin by going through a lot about vectors. So you might remember this from pre-calculus if you were taught it there. But one of the main components of Calculus 3 is we're going to take the stuff that we're used to in Calc 1, we're going to extend it into a three-dimensional space as instead of 2D, which is what we're used to. And then we're also going to talk about how vectors play a role and go into something about called vector calculus towards the end of the semester. So we're going to begin just by going through all of the basics. In case you haven't seen this before, we're going to talk about what a vector is, what are some properties of it, how do we break it down into different components. So if you've had physics before, you are also used to vectors there. So really a vector is an object that's used to indicate some kind of quantity that has two things. It has magnitude and direction. And all magnitude means is some kind of size. So typically we use vectors for force. It indicates the size of force acting on an object. But what we're going to do is we're going to represent these with an arrow or some kind of directed line segment. So I'm not going to write down every single thing that you'll see in my notes, so you can go in there to look at some extra commentary. But for this, a vector, we have some starting point A, we have some terminal point, which we'll consider B, and then we have an arrow to indicate the direction that this vector is pointing. So what we do is we typically use U and V. One thing I would highly recommend at this point, if you don't put a little foot on your U, definitely get into a habit. Otherwise, you are going to have some serious issues later on in the future. But also to indicate that this is a vector V, we want to put an arrow over top. You can use a full arrow, but typically what you're going to see is kind of just a half arrow over top of it. So this vector AB which is also what we're calling V. And again, we put the arrow to indicate it has this direction. This has initial point A and terminal point B. So the length of this vector, which is basically just the distance between these 2 points, is representing its magnitude, and the arrow is pointing the direction that the vector is heading. Now we do have a special vector, which is our zero vector. So the zero vector, which is indicated by 0 with that arrow over top, is a vector with length 0 and with no direction. So because we're working with some kind of different object, we're going to have different properties that are going to hold. Some of the operations will still work. So you can think about adding two vectors. If you have two forces acting on an object, those combine to either create a different force, but if they're acting in opposite directions, it kind of cancels each other out a bit. So these are operations like adding and subtracting. But it doesn't make sense to multiply two vectors together. We're going to talk about operations that you can think of as multiplication, but it's not so simple or straightforward. But one thing we can do is we can always amplify how much a force is acting. So maybe I'm going to double my strength and I'm going to make this vector twice as long. That's something I can do. And what this is called scalar multiplication. So we're going to be really specific about something that is a vector versus something that is a scalar. So just to kind of summarize that, some of our standard properties hold. Like addition and subtraction. But we can't multiply or divide two vectors. Okay. So however, what we can do is we can multiply vectors by a real number. Okay. So we call these kind of numbers just a set real number, a scalar. To distinguish them from our vectors. So to give you kind of a formal definition for the scalar multiplication, we're going to let C be a scalar, meaning it is just a real number. So 5, 6, 7, -2, -pi, they can be irrational, just a real number. Then the vector C times V is called a scalar multiple of V. Oh, it'd be helpful if I could write. So if the value of C is positive, then what you're going to do is you're taking that vector and it's going to be C times as long as it was before. If C is negative, it's going to point it in the opposite direction and also lengthen it however much it needs to. So to give you some visuals, say our vector V is right here. It's got that starting point here, and it's going to point in this direction. If I take this vector and multiply it by -1, that scalar multiple would be -V. And all that's doing is it's really going to create the exact same length vector, but instead of pointing forward, it's going to be pointing backwards. If I go ahead and multiply this vector by a half, it's going to point in the same direction, but it's going to be half as long as it was. So it cuts it in half. And then say if I take this vector and multiply it by -2v, again, I'm eyeballing this, so it's not going to be perfect, but that's going to move into the opposite direction, which is here, and that 2 is going to double the length, so it will be twice as long. Okay. Now, when we talk about adding vectors together, there's a couple different ways that we're going to do this. We're going to talk about how I can break down a vector into different components, but visually there's two different things we can do to just add them. So say we're given two vectors. Let's call one U, and again, I like to put that little foot on it because it is important, which has starting point or initial point A, terminal point B, and say vector V ends where A left off, or U left off. So it starts at B, ends at C. Then vector W, which begins at A and ends at C, is just the sum of U and V. Okay. So to give you a visual of this, I've got my 3 points. Here's point A, and let's say point B is right here. Vector U starts at A, ends at B, and points in this direction. Then let's say C is up here. Then our vector V begins at B, ends at C. So here is V. Okay. Adding these two vectors results in something that creates a bigger force and has a different direction that begins at A and ends at C. You can see it gets a little muddy with all the arrows on top of each other, but this is what vector W looks like. It is U plus V. Okay. So this process visually is called the triangle law, because you can see the two make a triangle. And even if the two don't have the same starting and ending point, you can always pick one up and add it to the tail of the other to create this triangle. So to give you a visual of that just kind of nicely, because the iPad is great for this, say our vector U is right here, and our vector V is somewhere completely off, but looks like this. What you're going to do is you're just going to take one and plop it at the tail end of the other. And so here is vector V, and then you go ahead and create a triangle out of them, and here is the vector U plus V. Okay, so that's one way you can go about adding vectors together visually. A second way we can do this is known as the parallelogram law. And so all we're going to do is create a parallelogram from these two vectors. So let's say they don't have the same starting and ending point. Maybe here is vector U, and let's say here is vector V. I'm going to go ahead and I'm going to duplicate these. So here is vector U, and then I'm going to take vector V and I'm going to create it so that their initial point lies on top of each other. Then what we can do is we can go ahead and create a parallelogram out of these. Let's see. So we go ahead and draw a parallel line here, a parallel line here, and connect it as best as we can. And then the way I add these two vectors is I go ahead and just create the diagonal between these two. So this right here would be my vector W, which is U plus V. Okay. So this method of adding two vectors is called the parallelogram law. Either one, perfectly fine, whatever you want to do. Now, if you're subtracting two vectors, it's really the same kind of idea, because remember, a negative out front is just a scalar multiple, so it's putting one in the opposite direction. So let's say if we subtract two vectors, we can find the new vector, or find the resulting vector, geometrically using that U minus V is really U plus negative V. So very simple algebra from here. So to show you an example of this, let's say here is our vector U, and then we want to subtract the vector V, which I'll say looks like this. Well, negative V is going to be the same exact vector, same length, but it's going to point in the opposite direction. Okay. So I'm going to go ahead and duplicate these. Here is U, and I'll do the triangle law for this one. Here is vector V. We go ahead and do the tail end of one on the other. And I should have made this a little bit of a bigger angle, but that's okay. Make it work. This is negative V. This is vector U. So creating our triangle, we go ahead and connect the dots here. and this will be our vector u minus v. Okay. So this gives you just a rough idea of how these work together, how they result. Again, it's really useful in physics and the idea of forces. But really we want something that's a little more substance to it. So we want to talk about how can I really think about these in terms of in a plane. So maybe in the XY plane or the XYZ plane that we'll introduce here. And so we're going to talk about something called a position vector. So a vector, which will again be v in R2 or R3. And again, that just means two-dimensional plane or three-dimensional plane with initial point at the origin. Is called a position vector. So to give you a visual of this, R2 again is just our XY plane. Here is X, here is Y, and our position vector is going to start at the origin and have some terminal point in one of these quadrants. Let's just make it quadrant 1 to be easy. So this is vector V. So what we're actually going to have here is this has some ending point. I'll call it A1 and A2. Okay. We know that we can make nice right triangles out of this, so we can drop a right angle down. A1 is the distance it travels in the X direction. A2 is the distance that it travels in the Y direction. Now for 3D, we're not going to spend a ton of time graphing these yet. We're going to dive pretty deeply into working with graphs of functions in 3D and introducing stuff a little bit later on. But for now, what you have is to add a third dimension, you basically need a point coming off into that 3D. So you've got your flat surface, which is the XY plane, and we call Z to be this third component. So the way we typically like to graph this is we have to do it at some kind of angle. So here is our XY plane. And you would continue these backwards. So that would be that flat surface. And then Z is going to point directly upwards. And then you would continue it below. So that's our best impression that we can get for drawing this thing in 2D, even though it's 3D. So for these position vectors, it's going to start at the origin, and it's going to have some ending point, which is going to now be a triple. You have the X coordinate, the Y coordinate, and then the Z coordinate. That's the very nice thing. Everything is going to typically go alphabetically. And so this will be our vector V. And again, you can still do right angles. Z is, or the Z coordinates, how much it moves up in the Z direction. First coordinates, how far it moves along the x-axis. Second coordinates, how far along it moves in the y-axis. So where it ends is super important for us. So the terminal point here is either A1, A2, or a triple A1, A2, A3. Okay. And again, because you're starting at the origin, this is exactly how far you're moving in the X, the Y, or the Z component. So these coordinates are called the components of V. So what we do to indicate how far it's moving in horizontal, vertical, and then in the Z direction is we write our vectors really as follows. So we say vector v is going to be composed of two different things. To indicate it's a vector, we use these brackets here. In the x direction, we move a distance of a1. In the y direction, we move a distance of a2. So this is what our vector will look like in 2 dimensions. Or the vector v in 3D will again be a triple inside of these brackets. So a1, a2, a3. So your notation is super, super, super important in this course. Just like if you had me for Calc 1, especially in person, I really harp on you using the integral sign and ending in that dx. And even if you took me online, I harped in those comments about it because this is really fundamental here now that we're moving into these higher dimensions. So your notation has to make sense here. So when you're talking about a vector, you have to use these particular brackets. If you're talking about a specific point, that's when we're using these parentheses. So you want to be really, really, really cautious with that. Okay? So we're always going to use these angular brackets to indicate a vector or to denote a vector. And we're always going to use parentheses to denote a point. So be very, very, very conscientious of that. Now that we have these components of a vector, we can actually dive deeper into what is it, the magnitude, and also very soon, what is this direction going to be? So remember the magnitude is going to be the size of the vector. So this is what we can also call the length. The length of the vector v is exactly the magnitude. So this is called the magnitude of v. And it's denoted by one of two things typically. So to say you want to take the length or the size or the magnitude, these are all very similar words. What we're going to do is we're going to put this v in those absolute value bars because that's really what this is. It's giving you a distance. So in normal, way back in Calc 1, pre-calculus, college algebra, the absolute values gave you the distance from, or the distance or size of something. It's the same idea here. It's just a little bit more complicated. So this is the notation that I'm typically going to use just purely because it's easiest to write for me. However, what you're going to see in a lot of books and sometimes in your homework, and typically in your homework, I believe our book uses this notation more, just so it doesn't confuse you. Instead of doing one set of bars, you do two. Okay? You might also hear this called the norm. So if you're going on to linear algebra, you're going to talk about that pretty heavily here. But this is an operation that can exist in a lot of different spaces. So this is telling us the size of this vector. So really all it is it's going to be our distance formula. So in 2D, we have the following. So typically I'm going to show you it in 2D if possible, and then it's going to have a really nice extension to 3D. So our vector v starts at 0, 0, and it ends out here at a1, a2. And then we've got that straight line connecting it. So here is vector v. So if I want the length of this vector, all I'm going to do is make a right triangle. This side length here is going to be a2, it's the vertical distance, and this side here is going to be a1. So if I want the length of this vector, really Pythagorean theorem, or the distance between the 2 points, one side squared plus the other side squared is the hypotenuse squared. The hypotenuse is the length, so we just take a square root of that. So in 2D, we have our vector v has the components a1, a2. So the length or magnitude of v is going to be you square each component, add them together, and then you take a square root. When you do 3D, it's a natural extension. The distance formula is going to just do exactly what you want. So in 3D, we have the following. The vector v has three components, a1, a2, a3. So the magnitude, the length, the norm of v is you take each component, square it, add it together. So you just add that third one in, and then you go ahead and take a square root. Okay? Now the problem is in real life, this isn't typically going to happen where our vector is going to start at the origin. Instead, it could be just happening in space somewhere. So in that case, we have a really natural transition as to what we do to find the components of these vectors. So in general, most vectors won't have their initial point at the origin. So let's suppose that v has initial point a, which is some x, some y, some z, and we'll indicate with subscripts to be our starting point. And then it has terminal point b, which has the coordinates x2, y2, z2. Okay. Then what I want to find how far it's moving in the x direction, the y direction, and the z direction, I just subtract the two. So our vector v is going to be found by taking our terminal x value and subtracting the initial, and that's how far it moves in the x. y2 minus y1 is how far it moves in the y. And z2 minus z1 is how far it moves in the z. Okay? So really, hopefully, naturally, what you would think would happen. And to just give you a little example, let's find a vector represented by the directed line segment between A, which has coordinates 4, 0, negative 2, and B, which has coordinates 4, 2, 1. So we'll call this vector V, which starts at A, ends at B, and it has three components. So we take all of these different B values and we subtract the A values because we're starting at A and ending at B. So for the first one, B ends at 4, and we subtract A value, which is also 4. B ends at 2, and it starts at 0, and then the Z component, B ends at 1, and A starts at negative 2. So subtracting these out, our vector V moves nothing in the X direction, moves 2 in the Y direction, and then moves 3 in the Z direction. So hopefully it's a pretty natural extension then. If I want to add vectors, you're really just going to add component-wise. If you want to subtract vectors, you subtract component-wise. And then if you're doing a scalar multiple, when you take a vector and times it by a scalar, it just lengthens each component by that much. So you multiply inside the component. So to summarize this, so now how do we algebraically add vectors? If our vector A has components, we'll just do this in 2D, and again, it extends to 3D. If A moves A1 in the X, A2 in the Y, and vector B has components B1, B2, then, oh, don't know what my pen just did there. If I take A and I add vector B, all I'm going to do is add component-wise. So we do A1 plus B1, A2 plus B2. If I do subtraction, A minus B, we subtract those components, the like ones. And then if C is a scalar, then if I take C times vector A, all it's going to do is scale each component. So you take whatever was in the X and multiply it by that scalar. Whatever was in the Y, multiply it by that scalar. Okay? And then the exact same thing holds for 3D. So let's try an example, and we'll go ahead and tie it back to that magnitude. Suppose if U has the components 2, -4, 4, and vector V has the components 0, 2, -1, we're going to go ahead and find U plus 2V, and we're going to find the magnitude of this vector. Okay. So before I can find the magnitude, I've got to go ahead and I've got to find the thing on the inside first. So we need to figure out what is the vector U plus 2V. And I'm going to add more steps than you probably need right now, but just to keep track of everything, it makes it a little bit simpler. So our vector U is 2, -4, 4. And then I want to go ahead and add 2 times the vector V, which is 0, 2, -1. So I'm going to go ahead and I'm going to do this multiplication, meaning each component is going to double. So I want to take 2, -4, 4, and I want to add, when you do 0 times 2, it's 0, 2 times 2 is 4, -1 times 2 is -2. Okay. You can absolutely skip this next part, but I'm going to go ahead and add component-wise. So we need to do 2 plus 0 for that first part. Then we've got -4 plus 4 for the second. And then for the third, we've got 4 plus -2. And then simplifying this, 2 plus 0 is 2, -4 plus 4 is 0, and then 4 plus -2 is 2. Now that we've got the vector, we can go ahead and find the magnitude. So again, all that means is you take each value, square it, add it together, and then we go ahead and take the square root of that. 2 squared is 4, so this is 4 plus 0 plus 4. This gives us the square root of 8. So the length of this vector is the square root of 8. Okay. I don't mind on your test if you don't simplify. Typically, the online software is pretty good with you not having to simplify either. So perfectly fine if at any point you get marked wrong on like a test or something because you didn't simplify, just let me know. Now that we've got a little bit of familiarity with all of these operations, I'm going to go ahead and go through all of our different properties. Just like we have properties with real numbers, same thing is going to hold here. So let's talk about the properties of vectors. So we're going to let u, v, and w be vectors. And we're going to let c and d be scalars. Then the following is going to hold. First, if I take vector u and I add vector v, just like 1 plus 2 is 2 plus 1, same exact thing is going to hold for vectors. So it does not matter the order that you add these to. You can flip it around. Second thing is if I'm taking vector u and I'm adding v plus w separately, just like with numbers, you can go ahead and switch the order that you do this. So instead I can group it as u plus v and then add w afterwards. If I take any vector and I add the 0 vector, just like when I add 0 to anything, it does nothing. Same idea here. You land with the same starting vector. If I take vector u and I add negative u, those are pointing in the opposite directions. They have exactly the same value but opposite signs. Everything is going to cancel out and land you with 0. But not just 0, it is going to be the 0 vector. So be careful here. When I add two vectors, the result is a vector. So I need to make sure I put that little hat on top of it. Next one has to deal with the distributive property. If I take c and I go ahead and multiply that by u plus v, you can absolutely distribute that. So do c times u plus c times v. And then in a similar note, if I'm doing addition of two scalars out front and then multiplying the vector afterwards, you can distribute that vector out. So this is the same as cu plus du. The next one, if I'm going to go ahead and multiply two scalars and then multiply that by our vector, I can instead do one of the scalars times the vector and then multiply by the other scalar, or I can also switch this order. Makes no difference. And then our very last property, if I take 1 as my scalar and multiply it by the vector u, it just results in the same thing. Because if I do 1 times anything, it lands me back at 1. Okay. So these are our properties. Again, you can use them. You might use them without even thinking about it, but it's just to kind of show that this is a complete system. So anytime we're working with some kind of operation or a space, these kind of rules are going to have to follow. We have to be able to commute the addition. We have to be able to distribute things. So just be conscientious of that. You'll kind of see it as a reoccurring theme within mathematics. So now we're at a point we can talk about some really special vectors that you're going to see pretty frequently in here. So in total, there are 3 vectors that are very important to us. The first one is the vector which we call I, and it has components 1, 0, 0. Then we have the vector j, which is 0, 1, 0. And then finally, the vector k, which hopefully you see the pattern, is 0, 0, 1. So these vectors have a 1 in one component, 0 everywhere else. The reason that these are super important to us is because there's something called a basis vector. And what that means is they're going to be able to be used to write every other vector in that space. So you can also have different basis vectors, but these are kind of the most common simplistic ones. So these specifically are called the standard basis vectors. So they have length 1, which is super nice. You know, we like stuff to have a length 1 like our unit circle. And they point in the direction of the positive x, y, and z axes. So again, to give you that visual in 3D, we've got our x-axis that likes to point forward. We've got our y-axis over here. And then our z-axis points to the sky. We can add a scale on here. So say we'll make each of these have length 1. These are positive. And then if you were to draw these backwards like this, that would be considered the negative side of that axis. So to just kind of draw on top of this, our I points in the direction of the positive x-axis, and it has length 1. So this is I. J points in the y direction, and then Z or K points in the z direction. The reason that we really like these is because any vector, whether it's in 2-dimension or 3-dimension, can be broken down in terms of these. If you're in 2-dimension, then you're just dealing with I and J, and you're ignoring that Z component. So any vector that I have U, let's say it has components A, B, and C, can be written in terms of these 3 basis vectors. And to show you, we're really just going to split everything out. If our vector U has the components A, B, and C, using our vector addition, you can write this as A, 0, 0, plus 0b0 plus 0, 0, c. So you can always break it down into just that single component in each. And then using your scalar multiple, you can pop A out, and then it leaves you with a 1 in that first spot, followed by 0, 0. Then we pop out a B, and that leaves us with 0, 1, 0. And then we pop out a C. So really, the way I can always break down a vector is it's that first component times the vector I, plus whatever the number is in the second component, times the vector J, and then C times the vector K. And so this is why it's called a basis vector, because it is the basis for every other vector in this space. So super nice. You'll have to also get used to using I, J, and K because you're going to see kind of interchangeable depending on the problem. It might give you a vector in this first starting form component-wise, or it might break it down into I, J, and K. But again, these two terminologies mean exactly the same thing. Now we're just going to get back to some other properties and terminology. So I said these are a standard basis vector. They have length 1. Length 1 is super nice for us because, again, if you remember, it's very easy to scale up or scale down something with length 1. So those are what we call unit vectors. So a unit vector is just a vector whose length is 1. Okay. So for instance, I, J, and K, these are all unit vectors. You can also think anything on the unit circle. If it points to a vector in that spot, it has a length of 1. So we really like stuff to be unit. But again, typically most vectors are not going to be unit. But what you can do is you can always find a vector in the same direction that has length 1. So say your vector has length 5, well, then all you're going to do to find a vector of length 1 is you're going to scale it by a fifth because you've got to cut it down by 5. So once you know the length of a vector, you can find something that's unit in the same direction by dividing each component by that length or that magnitude. So to summarize that, in general, if our vector A is not the 0 vector, because that has length 0, then the vector that has the same direction as A with length 1 is the following. Our vector U is going to be, you take vector A and we need to scale it by 1 over whatever the length of A is. So you can think of this, you're going to take vector A and you're going to divide each component by the length. The reason we can do that is because we know the length of A is positive because it's not the zero vector. And it is just a number, it is a scalar. Okay? So to give you an example of this, let's find the unit vector in the same direction as V. Which has the components -4 to 4. So what I need to do first is I need to figure out what is the length of V. Maybe I'll get lucky and it is unit, but unlikely based on the components that I see. So the length of V, or the magnitude, is going to be, we take each component, square it, and then we take a square root. -4 squared is 16, 2 squared is 4, 4 squared is 16. 16 plus 4 is 20, add another 16. This gives us the square root of 36. So thankfully, this is nice. The length of this vector is 6. So knowing that this is the length of V, I'm going to go ahead and I'm going to divide every single component by 6. So the unit vector which we call U or unit, in the same direction as V, is the following. We're going to take V and we're going to divide it by the length of V. So really I'm taking the vector -4, 2, 4, and I'm dividing each component by 6. So just to simplify, really everything's divisible by 2. So -4 over 6 really reduces to -2/3. 2 over 6 is 1/3. And then 4 over 6 is also 2/3. Okay. So this length should be 1. And it seems much more reasonable because I can't have a component of 5 and it be a length 1 vector. They're all going to have to be fractions in between 0 and 1. So just to show you that this did work out correctly, if I go ahead and find the magnitude of U, that's -2/3 squared plus 1/3 squared plus 2/3 squared. And then we're going to take the square root of that. 2/3 squared is 4 over 9. 1/3 squared is 1/9. And 2/3 squared again is 4 over 9. Because these have exactly the same denominator, we really just go ahead and add the numerators. 4 plus 1 is 5, plus another 4 is 9. 9 over 9 is 1, so the square root of 1 is indeed 1. So we have indeed created a vector of length 1. So the very last thing we're going to do in this section now is we've covered what the magnitude is, that size, how to find it based on the component. Now we want to figure out what is going to be the direction. And so we're really just going to work in 2D for this because it's not as easy with 3D. But we're going to talk about how it can also find the horizontal and vertical components of a vector. So trig is super, 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 super important in this class. And this is where trig is going to first make its appearance. So as you can see, we can create a triangle with this when we're talking about a position vector. And again, we can always take a vector and move it to that origin, still has the same length. And that will tell us what angle this is creating with that x-axis. So anytime I have a vector in 2D, let's say it looks like this. Here is our vector v, which has components a, b. We know the hypotenuse here of our triangle is the magnitude of this vector, which is just that length. And then I can go ahead and I can drop a perpendicular line down. This is going to be A, how much we move in the x direction. This is going to be B. So our direction is going to be this theta value. It's how far we're moving from that x-axis. So just kind of working with our standard trig, if I go ahead and take cosine of this angle, it's the adjacent over the hypotenuse. So utilizing that, cosine of theta is going to be A over the magnitude of V. Rearranging this then, my x component is going to be the magnitude of the vector times cosine of the angle it makes with the x-axis. And then in the same manner, if I take sine of this angle, that's opposite over hypotenuse. So sine of the angle this vector makes is the component b over the hypotenuse, which is the length. So really, my component b, this should not be a little hat over here, a is just a scalar, is the magnitude of v times sine of theta. So really, your vector v can be written in terms of the length and the angle that it's making with the x-axis. So this component is the magnitude of v, cosine of theta, magnitude of v, sine of theta. And it's exactly what you would expect because cosine deals with the x, sine deals with the y. When we get to 3D, it's a little bit more complicated what that z component is going to be. We're going to talk about it at a future date, but for now, we're just going to stick with the 2D version of this. So let's just do one last example. Let's go ahead and we're going to find the magnitude of the horizontal and vertical components of v. Given that the angle this vector makes is pi over 4, and that the length of vector v needs to be 4. So again, magnitude is just talking about the size. This is basically asking what are the horizontal and vertical components. So my vector v is going to be the length times cosine of the angle this vector makes. My y component is the length times sine of the angle this vector makes. At this point, you do want to be really fluent in your trig, being able to evaluate these pretty quickly. You don't want your unit circle or have to have that out for every single thing. You do want to be pretty fluent in this. So pi over 4, it's the same for sine and cosine. That's our root 2 over 2. And since it's in quadrant 1, both of these are positive root 2 over 2. And then just simplifying this a little bit, before root 2 over 2, you can simplify. This would have components 2 root 2 and then 2 root 2. This one would be the magnitude of the horizontal component. This will be the magnitude of the vertical component. So we'll continue to expand our ideas about vectors and properties and things we can do with them in our upcoming sections.